thank you for joining us for this session today. Both Tori and myself are extremely excited to be here. It's our first time in the DSF. We're going to be talking about the application of graph analytics in financial services. Um, we thought it'd be a good idea, really, to put a poll out there to our audiences just to gauge what your experience or feel for graph analytics is. I think that is starting in the background. So it'd be nice just to see what your responses are to that. So while you answer the poll, I'll carry on. So just a bit of background about Advancing Analytics. Tori and myself work for a wonderful company, Advancing Analytics. We're a UK-based consultancy, and we deal with anything analytics, really, from big data right through your artificial intelligence. Now, for the given company size, I'm really proud to say that we've got 4 MVPs within the company. And we've got a Databricks beacon. It's Simon Whiteley, who's the other director of Advancing Analytics, actually. And I think from the top of my head, there's only 13 globally awarded beacons, and Simon's one of them. So you're really proud to be part of the company. We're also a partner with Microsoft and Databricks. So I'll let Tori introduce herself.
Hi everyone, I'm Tori. I'm a data scientist at Advancing Analytics. I have a bit of a background in cybersecurity, but I spent the last 3 years in the data science industry. In my spare time, I help run a company charity called Girls Code 2, where we go to schools and introduce them to coding.
Thank you, Tori. So I'm Gavi. I'm a principal data scientist. I actually did my PhD in experimental fluid dynamics many years ago, which I had my first taster into the world of analytics and AI. So in my spare time, when I'm not busy juggling my family life, I love getting involved in Kaggle competitions. And I'm also a STEM ambassador where I go into schools and talk about the world of artificial intelligence and machine learning. So before carrying on, really, I just wanted to give you a bit of motivation as to why you should stay and listen to us talk about this interesting topic. So the first key point is that Tori's worked really hard to come up with a really cool demo, and she shows how she applies graph analytics on a real world problem. So I'm not going to steal her thunder. I'll let her introduce that in part 2. The second point really is I wanted 2 minutes of your time over the next couple of slides to really see why graph analytics is important. So moving on, graph technology is the future. And this is not my words, really. This has been picked by Gartner, who's an independent consultancy that do research in AI and machine learning on all the new emerging technologies. And they've said graph technology is indeed the future. It's growing rapidly in terms of popularity and its usage. So they have shown figures back in 2018. Most of Gartner's inquiries on artificial intelligence and machine learning were about graphs, and only 5% were about graphs. Now, this figure has since grown to 50% in 2021. Now, their prediction is by 2025, graph technologies will be used in 80% of data and analytics and innovation. So you might be wondering whether graphs are new or not. And I can say graphs are not a new technology, right? They've already been used for quite a while at the top FANG companies. And they're not limited to the FANG companies. They've also been used in other tech companies. So your FANG companies are your famous Facebook, Amazon, your Apple, your Netflix, and your Google. So you might be wondering, right, how have they been using graph analytics, right? So let's look at Google. Your Google search, the technology that sits behind your Google search is powered by graph analytics, and it contains about 5 billion entities. Amazon and Netflix, 2 of my favorite companies that are used in this household quite a bit, their recommendation engines are powered by graph technologies as well. And a quick fact for everybody listening to this call, with Netflix, 80% of their shows that are watched by their customers are discovered through their recommendation engines. So what I'm really trying to show you here is all these companies have implemented graph technology very successfully to maximize their revenue, and not only to maximize their revenue, to also provide value to their customers. So hopefully you're still listening to us, and you're going to carry on listening to us. And if you are, I'd just like to talk about the history behind graphs. So graph theory may actually be traced back to 1736, so quite a while back now. And it can be traced back to an old Prussian city called Königsberg. It's no longer called Königsberg, actually. It's actually now called Kaliningrad, and it's in part of Russia. And out of interest, I was just interested to see where this particular place is. So I've got a map here showing where Kaliningrad is. It's sandwiched between Poland, Lithuania, and Belarus. Now, in Kaliningrad, there was a river that flowed through the city that divided the city into four main areas, right? So you had your north area, which is number 3, your south, 4, and your 2 islands separated by the river, 1 and 2. So to allow people to move from one particular area to another particular area, they built 7 bridges, which is highlighted in this yellow little diagram here on this diagram. So that's where the 7 bridges of Königsberg has come about. Now you might or might not have heard about it, but it's quite a notable puzzle in mathematics. And the puzzle was all about, can you cross each bridge only once and return to your starting point? I thought this was quite fun, really. So I pretended to transform myself back to the 1736, and I attempted to come up with a solution, right? So as you can see, I've come up with quite a few solutions, but none of them really solves the puzzle. The red line shows the trajectories through the bridges. Most of the time, I'm only crossing 6, and all the solutions I've presented here, I can never get back to the starting position. Now, secretly, I'm quite happy about this because I'm not the only one that was not able to solve this puzzle. The citizens of Königsberg could not invent a route that would allow them to cross each bridge only once and get back to the starting position. So what they did was they sought assistance from a famous Swiss mathematician called Euler. Now, being the clever man he was, he abstracted the puzzle in a very simple form. And what he did was he represented each of the land masses as nodes. So you'd see 4 blobs of nodes on the slide. And every bridge that connected the land masses were represented as edges. So this is what you see in the diagram here on the bottom right. This led to the foundation of graph theory. And using graph theory, really, he said there was no solution to the puzzle. So we've spoken a bit of graph, but now let's find out what graph is really, what's it all about? You know, what is graph analytics? And if you were to look up the definition in textbooks in really high level form is about graph analytics shows a relationship between data points. So here I've got a nice diagram that shows what that means. So you might have a number of tables that link up information. You can take all these tables and represent entities as nodes, which are shown as in your slide here, in your red dots. And the relationship between the tables are represented as edges. Graph analytics are also known as graph algorithms and network analysis. So you might hear this interchangeably as we go through this presentation as well. So I've given you a really high level definition as what you might find in textbooks. But what I really wanted to do is to provide some real world examples on how you might use graphs and build up our understanding. So here I've got a map of London, right? And Tori was very kindly decided to invite me out to drinks to South Kensington. I happened to be in Camden Town doing some shopping. So I evaluate very quickly my modes of transportation in London and how can I get to South Kensington? So I don't really know London that well. So I thought, okay, let's look at timetables. Let's look at buses. How can I get from Camden Town to South Kensington? I immediately realize that there's no direct routes. I've got a couple of stopovers at a very minimum. So with these stopovers, I need to have a number of tables that demonstrate the timetables, the different stops, and I need to work out, how do I get from a particular position to South Kensington? So these timetables are very much like your standard relational database where information are stored in columns and rows. It's doable. I can do it, but I'll probably sitting in Camden Town for the next hour trying to figure out what's my best route. So with that, I decide to look at the underground map. So just very quickly, it just seems that I can look at it. I can look at my position being in Camden Town. I can look at Tori's position being in South Kensington, and I can very quickly decipher how to get from one position to another position. So hopefully you'll agree with me, but looking at this looking at this image, sorry, you can take the Northern Line as an example, get to Embarkment, do a quick change, and get to South Kensington. So that's one example of showing a routing using graph and networks. The other example that we really wanted to showcase was a recap on the introduction that me and Tori did before. So we both introduced ourselves and we had a slide showing different points of both me and Tori. I've taken those bullet points and transformed it into a table. That's another way that we could have perhaps described ourselves. Information, if I were to present to you in a table, is stored in columns and rows, like you can see on the slide. But it is difficult to see the interactions between Tori and myself. So if you took that information and represented the introduction using graphs or networks, hopefully you can really clearly see the relationship between Tori and myself. So for example, Tori and me both work in advancing analytics. We both support organizations that support women in technology. Now, you could not have crossed that using the slide or looking at the slide that we presented earlier, or even the table form. But using graphs, it's possible. So hopefully you'll agree with me, graph is intuitive, it's extremely meaningful, and it's insightful. And those were the two examples that we wanted to demonstrate to build up your understanding on graphs or networks. So moving on from those two simple examples, how can graphs be used in businesses and organizations? Now, many businesses do this already. Three of the nice examples that we wanted to demonstrate were, for example, in transportation, graphs can be used very effectively in social networks and supply chain networks. Essentially, graphs are useful in addressing complex relationships in a network. So if you've got lots of interconnectivity and relationships, graphs really are a powerful method to do this. So going back a couple of slides now, if you remember the slide about the history of graphs where Euler used nodes and edges to abstract a simple puzzle, let's try and use those nodes and edges to with graph to model, say, for example, an airline network. So if you've got an airline network here, and if I was an owner of an airline, I could perhaps use nodes to represent different airports in the whole map. I could use the routes from one airport to another airport. I could represent that as edges. And this is how you'd start to use graphs and networks in businesses and organizations. Another example is in banking. You'd use nodes to represent account holders, and the transaction between account holders can be represented as edges. So those were about graphs, but to really get insight into graph, you'd need to use graph algorithms, because graph algorithms help make sense of connected data. And there are many, many algorithms out there. But what we really wanted to talk about is the three most common algorithms used in industries, and they are the shortest path, centrality, and community detection. Now, Tori's going to go into a bit of this in detail in her demo, so I don't really want to take anything from her, but just high level, a shortest path as an example, would help you find the shortest path from Camden Town, for example, to South Kensington in the quickest time. Centrality is one of my famous algorithms. It's been used by Google quite a lot to rank pages. Community detection is all about evaluating how groups are clustered and partitioned, and it's used very effectively to make product recommendations. So let's talk about the use cases. The title of this talk was how we could use graph technologies in financial services. So if you recall, graphs are useful when addressing complex relationships in a network, where there's lots of interconnectivity or relationships between entities. Now, financial services are all about the relationships and interconnectivity, and this is why graph technologies are a perfect fit. And with that, it can be used in many different areas in financial services. So I've put 7 examples there. So it can be used in fraud detection as an example, risk management, recommendation engines, customer experience. But for the purpose of this talk today, we really wanted to talk about fraud detection and recommendation engines. So let's have a look at it. So recommendation engines, what are they? It's a system that's designed to recommend the most relevant items to a user or customer, right? Its recommendations at the minute are amongst the most popular applications to be implemented in organizations. And it's important because it maximizes customer value and it helps business to stay competitive. The reason why I like recommendation engines is extremely versatile as an application. It can be implemented in financial services, it can be implemented in retail, in healthcare, and travel. So how might you implement a graph technology for recommending items? And I've just come up with a quick example here. We've got Jane, Jack, and Jim, and they all are into NASDAQ shares. Okay, so let's take Jack here as an example. Jack only buys shares that are Apple shares. Jim, on the other hand, he buys Apple and Google shares. So recommendation engine works in the fact that just because Jim has bought similar items to Jack, he's similar to Jack, and therefore Google shares would then be recommended to Jack. And graph technologies are really effective at doing this, building out recommendation engines. So now let's look at the other use case that we want to talk about. I want to talk about fraud detection. Unfortunately, fraud detection is the most experienced crime in the UK currently. And there are many types of fraud detection, right? The fraud detection to do with VAT, insurance, and loan. Fraudsters are becoming more technologically advanced, and this is why we need to implement really current and technologically advanced fraud detection systems. The other fact of fraud is it costs £190 billion to the UK currently. And just to put it in perspective, the cost of fraud is more than what the NHS costs the UK. So getting a handle on it is really important. So here I've got a diagram to show an example of credit card fraud. Okay, we've got John, who's an innocent bystander. Unfortunately, a fraudster's got hold of John's credit card information, and he's replicated his credit card information many, many times. Okay, so what the fraudster has now done is use the stolen credit card in many different locations, and he's used it many times quite successfully. So how can we use graph technology to pinpoint where this fraud actually happened? So I'm really presenting a really simple example here, but if you can imagine in a real world fraud case problem, the network would be very complicated and massive. Graph technologies are very effective of mapping this out and figuring out where the disputed transaction happens, and it can target it right to the source. So this gives people the ability to stop fraud happening and to catch fraudsters. So this is one example. And there are many, many more examples of how you could leverage graph technologies in financial services or in fraud detection. Right, so you might be thinking, right, all that sounds really interesting, but how do I really get started with with graph analytics? And if you're an enterprise outfit, you might have already come across a lot of the famous um, companies out there. Perhaps you would have heard of Neo4j and Tiger Graph, but I've put other companies out there that offer graph technology and graph databases that can be used. However, if you're not an enterprise and you want to use something more open source, there are quite a few popular Python graph packages out there. Some of them are shown on the slide here. And I will let Tori now talk about network hacks a bit more and how she's prepared a demo for you all.
Thank you, Gabby. I will share my screen. Are you able to see that?
Yes, Tori.
Awesome. Okay, so this is a Python Jupyter notebook. I'm going to take you through how we have identified potential fraud in a fake data set of credit card information, addresses, phones, account holders, etc. So what I'm going to do throughout this demo is I'm going to be using pandas to query our tabular data, and I'm going to be using NetworkX for the rest of the demo, which is going to be how I build and query our graph data. So I'll start off by taking you through the data that we have. So I will take you through, this is our table addresses. So this is tabular data. And this is whenever we have an account holder that is associated with an address. So if our account holder buys something and gets it delivered to an address, they become associated to it. If they apply for a credit card loan and use this address as their address, then they then become associated with it. And we've done this with addresses, with phones. We've got this for cards. So when account holders use a card or whether they secure a card at a new bank. We have this with banks, IP addresses, and social security numbers. So we essentially have 6 tables which logs data associated with account holders. And we want to use this data to identify informational financial fraud. So maybe people or fake accounts applying for new loans of people that don't exist, which is a very difficult thing to do when looking at tabular data. If you look at this, it's not immediately obvious what's fraud. It's just numbers and rows and columns. So we want to use graph to query this. So I've built a graph called fraud, and I've saved this. So I've pre-made it and saved it as graph ML format, so graph XML. And using NetworkX, I can read this graph in and save it as our variable G. So G from now on is our fraud network. NetworkX has some functions out of the box that will allow you to do some summary statistics on your network. One of these is directed. So if we run is directed and it returns true, what we know about our network that I've just loaded in is it's a directed network. So a directed network or a directed graph is if the edges have a direction. So we would have those 2 nodes connected and they would be connected rather than with a line, but they'd be connected with an arrow. So they can only move in one direction. So we know that our network graph is directed. And this direction is the account holders can have cards or they can have social security numbers, but the cards can't have an account holder. We have another function called isWeighted, and this returns false. So we know that our graph network, our fraud graph, isn't weighted. So a weighted graph would be if the edges have a numerical value associated with them. So for example, if we were to plot an airline network and the nodes were our airports and the edges were the routes between airports, then maybe the edges would have miles associated with them, or they would have a length of time between traveling the stations associated with them. We don't have this for our one, so it's not weighted. We can also quickly query our number of nodes. So we have 3,447 nodes in our network. Each of these nodes are account holders, they are banks, they are phones, they are all of the information we have plotted as nodes. And we have 3008 edges. So the edges is the association between the nodes. So if the account holder is associated with a phone, then there will be an edge between that account holder and that phone. Network X also gives us out of the box this info function, and it tells us a lot of the stuff that we've already just learned. So we have a directional graph, we have our numbers of nodes and our number of edges, and it also introduces us this concept of a degree. So in graph theory, a degree is a value that a node can have, and this is how many edges are coming in and out of that node. So a node that is connected to 4 different things would have a degree of 4. If 3 of those edges were coming in, that would be a 3 degree in degree node. And if 1 of those edges was going out, that would be a 1 out degree node. Another way we can quickly see this as well is with a degree histogram. So if I were to plot this as a graph, our first item in the list is how many nodes do we have in our network that are connected to no edges, that have a 0 degree. And we don't have any of those. Mainly because if you refer to above, each table, the account holder has to be linked to something. We'll never have a social security number that isn't associated with an account holder. The majority of our networks, the 2,897 of our nodes, have a 1 degree. So this would be a social security number is associated with 1 account holder. And then we have, throughout the rest of the network, varying degrees of different node degrees. So what I will do is, all of this information isn't particularly helpful to us at the moment. It's a good way to get a high-level summary of our graph network, but the value that we will see will really come from visualizing our graph. So I've created this custom function here, which will allow us to draw our graph using the Network X draw functionality. And I won't go too much into it. All of this stuff here will just assign colors to our different node types. So our account holders will be in blue, our addresses will be in red, and so on. And this might take a little time because, again, we've got over 3,000 nodes. It takes just under a minute to draw this. But when it shows up, you'll see that we won't get an awful amount of clarity from it. There is just too many nodes and there are too many edges involved in this network that we won't see any patterns whatsoever. It will just be a big mess. So here. So where we saw in Gavi's examples of the subway that we immediately saw value just in visualizing the network, in this example, we don't. So I've broken down it a little bit further for us. So what I've done is I've found some examples of fraud and non-fraud in our network. So I've identified this node ID here as a simple case of non-fraud. So to show you this, I can convert our fraud graph into an undirected graph. So I remove the arrows and we turn them just into simple edges. And I'm using this node connected component functionality from Network X to identify all of the other nodes that this one node is attached to. And then using subgraph, I can just filter down our graph to the node and the node it's connected to. So here we have an account holder of Catherine Wallace, and they are associated with 6 different pieces of information. They have an IP address, a social security number, phone number, card number, bank provider, and an address. So this is what we would call a case of simple non-fraud. So non-fraud can also look a little bit more complicated than that. So this here is our example of complex non-fraud. So at first glance, you might think this looks a bit suspicious. There's a lot of edges, there's a lot of nodes going on. But if you look quite closely, they all have, so both our account holders both have separate card information, separate bank information. They have their own social security numbers. The only information they have in common is this address. And if you look even closer, you can see they've both got the same surname. So it's quite likely that they are family or married, and they cohabit in this one address. So this is a case of a slightly more complicated non-fraud. So if we want to look at fraud, I've identified this node here. So this is what we would call a simple fraud. So we have 2 account holders here in blue. They also share the same address, but they suspiciously share the same phone number, the same social security number, and the same IP address. What they don't have in common is card numbers. So this, at first glance, would be quite suspicious in that one or both of them maybe don't exist, and they have been created and they share information to secure different card loans. So this is what we would call simple fraud. And again, on that, we have complex fraud. So I'll show you this here, where we have a lot more account holders involved, and the details or the information, like the social security number, aren't always overlapping as much as here, where we have three accounts associated with one social security number here. Here we have two, so we know that we have one account holder that has maybe secured two loans with two different social security numbers. So this here has got quite a suspicious amount of overlap. So we would call this maybe a more complex fraud network. So we found these quite easily because I already knew that they were there and I knew exactly how to find them. But what we want to do is leverage graph algorithms to find these suspicious cases, find this potential fraud, without having to search each node separately, because there's 3,000 of them, and potentially in a real life scenario, there would be much, much more. So what we can do is we can leverage community detection. So NetworkX comes with this functionality called connected components. And what this will do, if we pass in our graph, our undirected graph, is it will find different pockets of mini graphs. So if you look at these examples here, this is a full graph, this is a full graph, and then these two are full graphs. These are all nestled into one larger graph. So we want to find all of the different individual separated graphs within our network. And to do that, we've used this community detection function. So connected components will return us those pockets of nodes. We can build a graph for each one of those, and we can store that in a list called individual graphs. And if I just give you a quick length of that, then we know that we've got 475 different fraud networks within our graph, within our larger graph. And I can just pick, say, number 70 at random, and I can show this one here, and this is the case of Gary Hall, and they're separate, all their information. And this, again, like above, is a case of simple non-fraud. So we now have 475 graphs to look through rather than just the larger one. But the benefit is that these are smaller, separated, and much clearer to look through. So we can start to leverage those graph algorithms on individual graphs now. So the main difference between this case of simple non-fraud and our cases of fraud is just the amount of nodes that are involved. So what we can do is we can calculate the nodes in every mini network and use that to flag potential fraud. So this is what I've done here. So for every graph in our list of individual graphs, I want to flag up, if the number of nodes in that graph is more than 7, then I want to flag this as potential fraud. So I can run that there, and it will build me a list of fraud networks that we think are fraud. And if I pick one at random, so the first one, we get this result here. So immediately, this looks quite suspicious. There's lots of nodes, there's lots of edges. But again, this is a case very similar to the non-fraud earlier, and that they've all got separate information. The social security numbers make sense, the card numbers, and IP addresses, they've all got separate information. The only thing they do have in common is addresses. And there's quite a reasonable explanation for 4 people to be associated with the same address. They all live together. So this probably isn't a very good example of using node count or using a graph algorithm to find fraud. So then next, maybe we turn to degree centrality. So Gavi mentioned earlier that centralities are algorithms that will calculate the importance of a node in the network. There are different types. We have degree centrality, we have betweenness, closeness, and PageRank. PageRank is what Google will use to identify which, in a whole network of websites, which are the more important ones. And they use that to rank your Google searches. In this example, we want to use degree centrality. So NetworkX has this really nifty function that will just immediately calculate the degree centrality of every node in the network. So I mentioned earlier that degrees are the count of edges in and out of a node. So the degree centrality is simply the count of the degrees a node has compared to the rest of the network. So if we've got 10 nodes in the network, 10 edges in the network, and we have a node with one edge, that would be 1 over 10. In this example, we've got a lot more nodes, the numbers are a bit more complicated, but we get a count, a percentage of how important that node is to the network based on degrees, with varying different numbers. So we have, for example, here, this is a slightly larger number, so we can say that this node is probably more important or more interesting to us than this node here. So let's use that to detect some fraud. So what I've got here is I've taken that function and I've sorted our new list that we've just built up, and I found the node with the highest degree centrality. I've used our community detection to find everything that that node is connected to, and then I can draw that. And here we've leveraged degree centrality to find a fraud network. We can see here that our nodes share social security numbers, they share addresses, we've got IP addresses in common, and they've all got their own card loans. So this is what we would then think is potential fraud. So we can use and leverage degree centrality in graph algorithms to find potential fraud within the network. And I find this particularly interesting for me is that it's taken us to build the graph and use this tiny bit of code here to find a case of potential fraud. If we were to try and replicate a similar thing in tabular data, I think we'd be here a lot longer. We'd have to know a bit more about what we were looking for. Maybe we think sharing social security numbers is really suspicious. So we'd have to query our social security number table to find suspicious account holders. And then from there, we'd have to join this to the IPs table. We'd have to join it to our providers, our card numbers, and we'd have to do a lot more querying to find a suspicious network than just this simple one line or one section here, which I think is pretty cool. Yep, that's me. Gavi, do you think I've missed anything?
Oh, that's great. Thank you, Tori. Yeah, and I think with that, it's the end of our presentation and demo. Over to you, David.
Perfect. Yeah, perfect. Thank you both very much. I can already see a few comments in the chat coming in to say thank you. So if you're watching along at home and you enjoyed that as much as I did, please do give us a little shout out just to let us know that there have been people out there around the world following along with us as well. So as we're doing that, there are a few questions in the Q&A. Quite a popular question in the chat and also in the Q&A is, are we able to get access to the workbook? Is that something that you guys are able to do or watch the video back?
Yep, I can share. I've got GitHub. I can share my link to the code in GitHub afterwards. Perfect.
Thank you very much. Really appreciate that. In terms of the comments coming in, I will jump to those because they are starting to come through, and it is always nice, isn't it, out there to know that there are people watching along. So first of all, oh my God, there's a lot of scrolling involved for this. So Eugene, thank you. Adrian Bandy, thank you so much for your talk and for your time. Mo, thanks, really helpful demo. Arnab, great talk. Thank you. Pranath, perfect. Love to see how this is changing and graph networks are coming through. Alice, thanks. That was a super clear intro. Awesome. Thank you for the great presentations. Very insightful. Thank you both. Thanks, really very well explained. Andrew, thank you so much for the excellent presentation from Connecticut, USA. So we are a global community today. So yeah, great to see you, Andrew. Thanks for joining. Jeffrey Payne, great presentation, and they're still coming. So I might jump back to the chat in a second, but for now we will tackle a few questions and go from there. So if you're watching along at home, it is possible to upvote the questions. So even if you haven't got a question of your own and you see another one that you like the look of, you know, please do give it an upvote, and then we'll go from there. I guess just to kick things off as those questions are coming in, one question that I had, I mean, obviously a lot of this is based on maths and graph theory, etc. You know, how much of that is needed to start working with graph analytics?
I can take that one.
Thank you.
it's always useful to know the maths behind algorithms. But I think based on experiences, Tori probably might or might not agree with me. It's always more important to understand what the algorithm is going to yield, understand what it's going to give you, have an expectation. And if you're using network X, like Tori demonstrated that before, it's quite easy to pick an algorithm that is suitable for your problem that you're trying to solve and use it. But it's always handy to just understand what the algorithm would give us. Do you agree with that, Tori?
Yeah. In my example, I didn't really go into the maths at all. It's more important that you understand what the algorithms are trying to achieve, and you've got libraries that will leverage that for you.
Perfect. Thank you both very much for that input. Taking a couple of questions from the audience now. The most upvoted question with 8 upvotes is from Fiona. Fiona would like to know, how did you build your graph network from the tabular data?
Yeah, the easiest way to build graph networks is called edge lists. So you might have heard this before, but this is, you can change and shape your tabular data to be an edge list. And an edge list is just recording in a tabular format a to node and a from node. So you can shape your data. And in my example, it would be, I'd have the node ID of the account holder. And then in the second column would be the node ID of, say, the phone item. And then I would build that up to a massive long edge list, send that off. Network X has a function called from edge list, and it will just build a graph straight from that.
Perfect. And is there any performance limitations or performance things that you need to be aware of? Because in a lot of the examples you've used, they're obviously massive organizations with billions of data points. Is there any tips in terms of performance when you're starting to work with graph databases?
Yeah, so Network X is a bit of an exploratory academic library. It's really good and it's really powerful for graph algorithms which aren't widely used but are quite complicated. But there are limitations for computation power because it's pure Python. You're limited to basically the RAM on your computer. There are other ways that you can explore graph, and one popular way that I like to use is graph frames in Databricks, and that's leveraging Spark and the massive compute power of Spark to build up graphs, and you can make really, really big ones.
Perfect. Thank you very much. Anything to add on that, Gavi? Or
No, that's
good.
Yeah,
Thank you very much. Thank you. Next question at the top there is from Lewis Wilkins. It's good to see you online, Lewis. I'm not sure if you played along on the quiz on Friday night, Lewis, but there was a number of people from BJSS that did very well on the quiz. So you're working with some good people there, man. So yeah, well done to all of them. Lewis's question was, how was the average degree under 1 if the histogram shortly after showed no nodes with zero edges, or did I misread the cell after that? So that was about halfway through, I think, your demo.
Yeah, I think the explanation for this is probably that it wasn't using the degree count, but more a degree percentage, in the same way that degree centrality would use degree percentage. Okay. Which would mean it would be a value between 0 and 1.
Perfect. Thank you very much. Question from Noor. Again, great to see you online, Noor. He was talking about wider graph network technologies. I think shortly after his question, actually, you did put up a couple of slides. But if you could tell us a bit more about, is there different use cases? What do you see out there in the commercial world? What are the options in terms of technologies?
Well, there's loads of options, and it all boils down to what's the problem, whether you have to scale, how big, what your problem size really. And we don't have a particular preference. We're biased towards Microsoft and Databricks at the minute, and Network X, that's quite popular as well. So yeah, perfect.
It was great to see that, actually, because personally, I was very aware of Neo4j, but I didn't realize there was all these others out there. So.
And there's loads popping out as well with, the popularity of graph networks and graph technology. There seems to be more and more companies coming out with different solutions.
Perfect. Thank you. Question there from Jagdish. Whether it's something for you or not, I know that this was a great demo of using graph databases rather than perhaps being specialists in fraud and stuff like that. But obviously, I'll ask the question anyway, and if you have any input, that would be great. So first of all, nice presentation. Can you please speak a bit more about what are some of the more complicated rules that are used to identify fraud, i.e. something more real world than multiple people sharing an SSN? Is there anything more that you can call out in terms of, you know, using this to detect fraud, or is this very much for the purpose of the demo?
So for me, we used fraud as an example for the demo, not because I've got a background in fraud, but because it's quite an interesting use case that everyone would immediately understand the benefit from.
Yeah, that makes a lot of sense. Yeah, and anything to add, Gavi, or we good with that?
No, I mean, you know, we picked the title and we thought fraud is most in a prevalent use. It's happening very in quite a scale at the minute, and it'll be a good example to work on. So we thought it would be a good demo to form. And
it was a perfect demo. It was a great use case and a great choice. And maybe Jagdish is working in a fintech and looking for some pointers or something. I don't know. Right. So the next question at the top there, it's had 5 upvotes, so we will go with that one for sure. How can I do the solution implementation at scale? A safe banking case customers share more than 100. So we did touch on this very briefly, but there's different technologies out there to allow you to, you know, depending on the use case, essentially, is your answer on that one.
Yeah.
Perfect. Thank you very much. Arnab, this will be one for you, Tori. Perhaps missed the very start of the talk, I don't know, but their question, really enjoyable talk. First of all, thank you. What does fraud.graphml look like? I'm not sure I understand what G is in the worked example. Does it define all the relationships beforehand?
Yeah, so I had built up the graph using an edge list previously, but because I wanted to focus more on the algorithms, I didn't show you that bit, but I'd saved that graph that I built as a graph ML document, which is basically a fancy XML. So on your computer, it will look like an XML document. In the code, G is a graph class of network X. It's read in that XML and turned it into a graph in the context of network X. Perfect.
Thank you very much for that. I'll take a few more chat comments. And then we'll jump into a few more questions. We've got about 6 minutes or so left. We tried to keep this to like a lunchtime session, which probably doesn't help for those joining in America, but it's lunchtime in the UK. So back into the chat we go. Thanks very much, Tori and Gavi, for the knowledge sharing insight. Very interesting. Sammy, thank you for the reply. I appreciate it, which is great. I've got a few questions coming in. Thank you for informing and educating us. Your explanation is clear and succinct. Thanks, really interesting. Thank you for a great presentation. The list goes on and on. So there's clearly been a lot of people out there enjoying your session today. We have got a question a bit further down, talking about further reading. You know, it's coming from John Owens. What would you suggest as, you know, further reading? You know, if someone wants to just dip their toe and start to get into graph analytics, where would they start?
I'd say Neo4j has got an excellent database of, I think they even distribute free books. They've got a huge library for beginners. So, or even if you want to know about a certain algorithm a bit more, Tiger Graph as well, they've got a good website and good solution use cases and how you might, what could you do with graph analytics and what kind of use case would be applicable. I found that quite useful as well. Most of the big vendors actually talk a lot about, you know, how to get into graph and give you a lot of resources.
Perfect. Anything to add, Tori?
Yeah, I think Gary's covered it. There's the Neo4j O'Reilly book, which is brilliant. I also, when I've done graph before, if I've come across a really interesting graph, NetworkX has really good documentation where it will list out all the possible algorithms and will explain what they mean and what they do. So if you wanted to just play around and see what algorithms yielded good results, just reading the documentation is a really good shout.
Perfect. Thank you very much. Question at the top there from Samantha Knights, which I think is a great question, actually. It was one that I was thinking to ask myself. Could you comment on design decisions for choosing graph technology over relational type technologies? You know, what are the trade-offs you know, is there particular use cases that are best? Do people have to be aware of anything when they're choosing to work with graph technologies?
Do you want to take this, Tori?
Yeah. So I think the benefit for graph is that if you've got a problem that is very focused on the relationships between data and not just the data itself, that's when graph really shines, and that's what it's pretty much designed for. One thing I would say is that, and it's a problem that a lot of people come across when they first start, is one graph won't solve all your problems. A graph should be built with a problem in mind. So whether you're looking for fraud or whether you want recommendations or the quickest route across London's tube service, you need to have the problem in mind when you design the graph to get the most value out of it. No one graph is going to solve all of your business's questions, like relational databases would do.
Yeah. Okay. Yeah, I understand. Sorry, Gavi.
I think just to add to that, you know, if you're working with many different tables and you see clear relationships and interconnectivity, that's a great hint that, you know, graphs are really powerful as well, where you've got connections between tables, complex relationships, graph comes in.
Perfect. This may be a stupid question, but I always ask them anyway, so bear with me. If it is stupid, please don't tell me it's totally stupid and we can just gloss over it. So in terms of how this works, then essentially you start with the relational databases. There's been a data model built, it's all been normalized, you've got a nice schema, all that sort of stuff, and then you will export that data out into a graph database, as it were. So it always starts with that relational model underneath it and you export it out. And
I think the different options actually. Sorry, Tori.
No, you go on.
So I'm aware that Neo4j builds on top of your current databases, and it takes information, you know, siloed and builds a platform on top of it.
Okay.
I'm also aware where you can go into enterprise graph solutions that we presented at the end of the slide, where you can start using it. So there are different options.
Okay. Thank you. And it wasn't a totally stupid question.
No, absolutely
bonus,
not.
Hey, bonus. Well done, Dave. Awesome. There's a couple of final questions. We'll do our best to get through these, and then we'll draw things to a close. So, question from Noor: can the model predict or rank networks as fraud versus not fraud? Prescriptive analytics. Is this fully automated, or is this an augmented model requiring humans in the loop?
Yep, so for my example, if we found that degree centrality was a really good indicator of identifying fraud networks, there's no reason why you can't just let that run in the background, and every time something comes up with a degree centrality that was suspicious, it would flag that up as fraud. I've also seen people build up a graph network of fraud cases, just like mine, and would calculate different centralities, different algorithms, and store that data as relational and send that off to a predictive model, like a classification model. And then that would leverage data science and the graph relations to predict fraud.
Perfect. That's awesome. Thank you very much. Two final questions then. I'll actually take the one from Andrew Middleton first. You may have briefly touched on it previously, and I know you've said graph databases aren't the best for every situation, etc. Andrew's question is: thank you so much for the talk, really interesting. How do you quantify whether a graph is good or not? Maybe come to you, Tori, while Gavi has a coughing fit.
It's a good question. I guess in the same way that you would quantify whether a relational database was good or not. If it's full of junk and it doesn't answer your question and it's untidy, then it's not a good model. If it answers your questions and it's tidy and it's easy to keep up, then it does the job. I wouldn't say there was any such thing as an excellent graph.
Yeah, you'll know
just
quite
one that
quickly
solves your problems.
whether it's painful or not, basically.
Yeah.
Yeah, okay, understand.
Yeah.
Final question there. We're pretty much bang on time. I often overrun by a minute or two, so we'll call this as being on time. Question there from Jagdish. Is there a way in which you can combine the graph analytics with supervised learning, i.e. use findings from graph analytics to label a response variable, and then use that in supervised learning? Is that a use case that you've come across?
Yeah, it's growing at the minute. I think a lot of people call it the ML graph analytics or the ML graph wall, where they're starting to use graph in exactly the way Jagdish has just asked the question. So yeah, we have come across, it's growing, and graph neural nets as well, that's coming up.
Perfect. As ever, very exciting times within the world of data.
Yeah.
So really interesting to see where everything goes with this over the next couple of years. Just going to draw things to a close. Again, just to reiterate, thank you both very much for coming to share with the community. Clearly a very well received talk, which was good. Both of you had excellent presenting style, really clear, succinct, as someone mentioned in the chat, in terms of getting that content a go, and in terms of the demo that you'd pulled together there, Tori, or both of you, it was an excellent use case to give people that starting point. So we will follow up with you, if that's okay, about that workbook, and we'll work out a way to get that to the attendees. But yeah, just to reiterate, thank you very much, and hopefully you enjoyed it. How was it for both of you?
It was our first time. Hopefully it's not the last.
It won't
not from my side, but yeah, I really enjoyed it. It's good.
Awesome. And Tori, it was good for you?
Yeah, brilliant. I could probably talk about graph all day long. So
I feel like this might be a future topic. Yeah, we'll have to get you back and maybe even do a deeper dive. It definitely seems, as I say, really, really popular. So awesome. Well, thank you all very much. I've seen a few people saying that they'll be there on Saturday. So if you are there, I look forward to seeing you. Please do come and say hello. But yeah, thank you for joining us today, and we'll speak to you all again very soon. So bye-bye for now.
Thanks, everyone.
Bye.